Good evening. I'm Andrea Poet. I'm Director of Programs and Public Relations for the Chicago Council on Science and Technology. I'd like to welcome you to Baseball, It's Not Nuclear Physics, or is it? We are presenting this program this evening tonight with the Chicago Public Library Harold Washington Center. I don't know how many of you have attended a program with Chicago Council on Science and Technology before, but we're a not-for-profit organization. We bring scientists directly to you. We work with national labs, leading academic institutions and museums, and we host programs on a wide variety of topics, about 30 per year. Information on our events is in the lobby. You can sign up for our mailing list or follow us on social media. For those of you who know someone who wanted to be here this evening and could not, we are live streaming this event, and it will be on our YouTube channel, C2ST TV. So please send the link, share it with anyone who you think would be interested. And please do silence your cell phones if you've not done so already. I would like to introduce tonight's speaker, Dr. Alan Nathan. Dr. Nathan has spoken for C2ST before. He was with us in 2013 at US Cellular Field for 2 events. They were packed. He is a fantastic speaker, as you'll learn in just a moment. He's Professor Emeritus of Physics at the University of Illinois. After a long career as an experimental nuclear physicist, he spends his time researching the physics of our national pastime. He's been interviewed by MLB.com, ESPN Radio, the Boston Museum of Science, Scientific American, 60 Minutes, and NPR, among many other outlets. He's modest, so he may not tell you this, but his work is at the heart of composite and aluminum bat regulation in the NCAA and Little League. And in fact, his work on the ball bat coefficient of restitution, or BB-core, is now the standard. Enjoy, and Dr. Nathan will take questions from the audience after his talk.
Well, thank you, Andrea, for the introduction, and thanks to C2ST and the Chicago Public Library for putting on this event. We're getting very close to the beginning of baseball season, and of course you all know how last season ended. And of course you also know who the principal architect of that great season was, Theo Epstein. Here he is, Theo Epstein, curse buster. So many of you know that before he did it for the Cubs, he did it for the Red Sox, which actually turns out to be my team. Now, some of you may know, but many of you may not know, that Theo Epstein's grandfather and great-uncle wrote the screenplay for Casablanca. So next time you see the movie, take particular note of that. Okay, so let me tell you, first of all, about the baseball physics connection. One connection is this curious fellow known as Moe Berg. Moe Berg was a journeyman catcher, Princeton graduate, speaker of multiple languages, and a spy for the U.S. during World War II. Many, many stories abound about him. There was this great book that I read a few years ago. I'm going to reread it sometime. The Catcher Was a Spy. Among other things, he attended a wartime conference in Switzerland for the purpose of confronting Werner Heisenberg, who was one of the fathers of quantum mechanics and was in charge of the German bomb program. And Moe Berg's orders were, if he was to engage Heisenberg in some discussion, and if he determined that they were really on the verge of making a bomb, he was supposed to assassinate him on the spot. Well, he didn't do that. Anyway, later in life, he met Albert Einstein. This was written up in the New York Times in 1994. And the story goes something like this. Einstein says, "Mr. Berg, you teach me baseball, and I will teach you the theory of relativity." And then after a brief pause, Einstein said, "No, we must not. You will learn relativity faster than I will learn baseball." Okay. All right, well, this is some references here. This is the way I got started doing this whole thing. I read this book, The Physics of Baseball, by Professor Bob Adair, who's a high-energy experimentalist, Background very similar to my own, although he's a bit older than me and not terribly active anymore. Some very nice things that he says in his book. Our goal is not to reform the game, but to understand it. That generally is what physicists try to do. The physics of baseball ain't rocket science, or you could substitute nuclear physics. It's much harder. So it's not the physics of, nice, neat things that they teach you in textbooks. It's the physics of everyday life, which generally speaking is much harder. So it involves creating models for yourself, making reasonable approximations, but never violating the principles of physics. Another book, a much more advanced book, is written by Rod Cross. This is fairly new, Physics of Baseball and Softball, that has a lot of new things that post-dated the book by Adair. So there's a lot of really, really interesting stuff there. And then my website is as good a reference as you'll find for almost anything associated with the physics of baseball. Okay, so here's what I'm going to talk about. I've got 5 separate little topics. Get a grip, and you'll see why I call them that in a second. Eyes wide shut, spinning out of control, swinging in for the fences, and if we don't run out of time, extra innings, Rocky Mountain High. All right, so let's talk about get a grip. I want to talk about more generally the physics of the ball-bat collision. So here is one of these photos of opportunity where the ball and the bat are right in contact with each other. It's a high-speed collision, very violent collision. You see the ball sort of wraps itself around the bat. Here is a little video that shows a ball fired at 120 miles an hour onto a steel plate. And one of the things you should note is that the ball really gets crushed, and then it bounces back a whole lot slower than it went in, lost about half its speed. So it's a very, very inefficient collision. Despite the fact that it's an inefficient collision, there are certain principles of physics that have to be obeyed. One of them is called conservation of momentum. You can really see that here. Here is Crawford, I can't remember his first name, for the Giants. Brandon Crawford, sorry, who's bunting the ball. Notice that the bat recoils back after the ball hits it. So the bat transferred momentum in this direction to the ball, so the bat pushed on the ball that way, the ball pushes back on the bat in exactly the opposite direction, so the bat recoils. You can see the same thing. This is a high-speed video showing the bat being swung. In this case, the recoil is not enough to actually push the bat backwards, but it does slow down considerably. You can look at you can just see by looking at the distance between adjacent markers here that the bat slows down after contact by a tremendous amount. And there's no way to prevent that. If you're a big, strong person, is it going to recoil less? That's part of the question that I want to answer. So the question is this: how much does the batter's grip on the bat matter as far as that recoil is concerned? Is a big, strong hitter, okay, who holds the bat tightly, okay, is that bat going to recoil less? Is that the ball going to be hit harder as a result of that? That's the question. So let me pose several questions. Is there less recoil with a tighter grip? Does the ball leave the bat faster with a tighter grip? Does the batter muscle the ball? You hear the announcers say this on TV a lot. Oh, he really muscled that ball. So these are the questions that I want to answer, okay? And to do that, I want to emphasize 2 key points. The first key point is that the bat is not a rigid body. I'll show you what I mean by that and evidence for it as we go along. And the ball-bat collision is very, very rapid. Okay, so those are the 2 key points. Let's see how those 2 key points enter into this discussion. Okay, the bat is not rigid, it can vibrate. So here is a ball hitting the bat on the sweet spot of the bat. This is Marco Scudero. There was a lot of high-speed video. I think it was at the 2012 World Series. So the Giants were playing. So I have a lot of San Francisco Giant things here. So here's Marco Scudero. And you see there's the bat slows down, but it's a nice, smooth transition. Okay, the bat slows down, but nothing funny is going on. I compare that with this. The bat hits the ball on the inside of the bat, inside of the sweet spot, and notice that bat vibrate. In fact, look at his hands. The bat almost gets knocked out of his hands. Same thing happens if you hit outside the sweet spot. Look at that bat vibrate. That's what I mean when I say the bat is not a rigid body. It can bend, okay? And hitting it off the ball hitting the bat off the sweet spot will make it bend. And of course, it's well known to the players, when the ball hits the bat on the sweet spot, it feels in your hands, it feels nice and, it feels like nothing has happened, okay? But when you hit it off the sweet spot, it vibrates and it stings. That's the vibration that you actually feel, okay? And you can see the same thing with broken bats. This is one of my favorite things to look at. Here you're hitting on the outside. So when the bat vibrates, there's actually a fixed point on the bat that doesn't vibrate. There's a second fixed point over here, okay? And the bat basically wiggles about those two fixed points. So if the ball hits the bat on the outside, the bat bends towards the pitcher, and that's the way it breaks. Because you see it cracks towards the pitcher. On the other hand, whoops, went the wrong way. On the other hand, if the ball hits on this side of the sweet spot, it bends the other way and it cracks the other way. So look at this bat and the way it cracks. You see it splinters in that direction. All right. So these are the sort of things that I look for when I'm watching a game, believe it or not. Of course, if the Red Sox are playing, I'm not looking at any of that stuff. I'm just, sitting on the edge of my seat. But, if I'm just watching any old game, I actually look for these things. And, oftentimes I come across something that, that looks interesting, and then I quickly go to my laptop and, pound out some calculations, and the next day I have written an article about it. All right, so here's a curious, so this really is now getting to the heart of the matter. So here is a bat, and here is a ball hitting the bat, and that's my hand there, okay, and this is a high-speed video, and here's what I want you to look for. So I'm hitting the bat right at the end of the bat. I want you to look at the motion at the handle. The handle starts to move only after a noticeable delay. A little wave ripples up that bat, okay? And in effect, what happens is a little wave ripples up that bat. It bounces off whatever up there, whatever is supporting it, and it bounces back down again, okay? And it does it, the amount of time it takes for that wave to go up the bat and back down again to the impact point is longer than the amount of time it takes for the ball-bat collision to take place. By the time that reflected wave gets back down here, the collision is over, the ball has already left the bat, okay? So if you think about it, nothing on the handle end of the bat could possibly matter as far as what happens to the ball is concerned. Not the knob, the handle, or the batter's grip, okay? And if you carry that one step further, the batter could just as well let go of the bat just prior to impact, and it would not make a bit of difference what happens to the ball. Do you believe me? Most people don't believe me when I say that. In fact, I have been saying this. This was actually the very first piece of real research I did in the physics of baseball, was really studying exactly this problem, vibrations and how they affect the collision. And this is one of the things that immediately pops out of the calculation. The physics is actually quite easy. The details are complicated, but the essence of the physics is easy. The bat is, the bat vibrates, okay, a wave ripples up, comes back down. It takes longer to come back down than it does for the collision to occur, so the grip can't matter. Anyway, I have been saying this for several years, many years, and then finally something happened a few years ago. Todd Frazier, who at the time was playing for the Cincinnati Reds, hit a no-hands home run. Notice that his top hand is completely off the bat and his bottom hand is almost off the bat at the time the collision occurs. He literally threw the bat at the ball. The ball traveled something like 380 feet for a home run. The grip simply did not matter. Okay, end of story, or almost end of story. I should answer these questions. Is there less recoil with a tighter grip? No. Does the ball leave the bat faster? No. Does the batter muscle the ball? No. End of story. Okay. Eyes wide shut. We're on to our second topic now. Batting and thinking. So Ted Williams This is the 1955 Topps set, a card from my personal collection, I might say. I'm a baseball card collector. Hitting is 50% above the shoulders. Hitting is, a lot of hitting is mental. It's looking at the ball, processing information, okay? Now, there's a I'm going to skip this, very complicated thing. This comes from Bob Adair's book about batting and thinking, and basically, let me just give you the bottom line here. What Adair said in his book, based not on any experimental data or anything, but just sort of his gut instinct, was that the ability of a batter to process information is somewhat limited, to process information quickly. And basically, if it takes 0.4 of a second for the ball from release to home plate, which is typical of a good fastball, about 0.4 of a second, the batter has the benefit of being able to react to about half of that time, but probably no more. First of all, it takes a 0.15 seconds, which is a significant fraction of that, just to swing the bat. But the ability to see information, for the information to go to the brain, for the brain to react, to go through your lookup table to figure out what the pitch is going to do, basically the batter probably can only benefit from roughly half the information, the first half of the pitch. And all his decisions and his ability to react is based on that. So this was, quote, theoretical. And it's only recently that that we are on the way, at least, to doing experiments that actually test this. So I want to tell you about an experiment that was done by a group of Japanese people. So I'm not telling you about any work that I've done. This is what they've done, but it's beautiful, beautiful work. All right, this is the paper, Contribution of Visual Information About Ball Trajectory to Baseball Hitting Accuracy. You can check the reference if you like. Here's the experiment. So they had batters hitting from a pitching machine. Fastballs and curveballs. They didn't know whether it was going to be a fastball or a curveball. They had special glasses that were liquid crystal glasses with electronic shutters. And these electronic shutters allowed the experimenters to essentially open and close the shutters so the batter could see or not see with an electronic signal. Okay? The batters hit under 3 different conditions. They call the first condition the no condition, in which the shutter is open for the full trajectory. They had the condition they called R plus 150, where the shutter closed 150 milliseconds after release. And remember, the ball takes about 400 milliseconds to get to home plate. And then they had A minus 150, where the shutter was closed 150 milliseconds prior to arrival at home plate. And what they wanted to do is compare the batter's ability to hit the ball under those 3 different conditions. Okay? Okay, so here is, let's see, they use high-speed cameras. So here is the bat. They use, and this is what they call the target. This is the sweet spot of the bat, which is about 6 inches in from the end of the bat and roughly centered up and down on the bat. Okay? That's where the batter was trying to hit the ball. Okay? High-speed cameras recorded the location of the impact on the bat with the goal of hitting on that spot. Okay? So, here are 2 different pictures. Okay? R plus 150 blocked out all of this. So the batter only saw this much. Okay? Only saw the first 150 milliseconds. Okay? A minus 150, the batter saw this much. Okay, arrival minus 150, all except for the last 150. And then the no was everything. Okay, so here is the result for the no. This is the target here. It's a little higher. Okay, so the batter was trying to hit the ball slightly on the underside. Okay, which is what you do if you're trying to get backspin on the ball. I'll say more about that later. Here is the R plus 150. Notice these things are pretty nicely clustered right around the sweet spot, and this is all over the place. This is the R plus 150, where the batter sees only the first 150 milliseconds and nothing thereafter. But this is the A minus 150, where the batter sees everything except for the last 150 milliseconds. Notice that this and this look very, very similar. That last 150 milliseconds did not seem to make a bit of difference to the batter, whereas this condition did. So here is the results. R plus 150, the batter is much less affected. A minus 150, these two are pretty much the same. The last 150 milliseconds provides no useful information. So the hypothesis that Adair had in his book seems to be confirmed. The batter could just as well close his eyes when the ball is 150 milliseconds from home plate. Let me skip that. We'll talk about something else in a second here. Oops. So in this bizarre world of physics, the outcome is not affected if the batter drops the bat, I've said that already, or if he closes his eyes, all right? So it really is true. Okay. And it really seems to be a fiction. You know, some people talk about the batter being able to track the ball with his eyes all the way in and see the ball hit the bat. And there's no way that could happen. Absolutely no way that happened, because when the ball gets really, really close, your eyes have to turn through a very big angle in order to see it. It is possible to see the ball hit the bat, but to do that, you have to take your eye off the pitch and look at where the impact location is. But you can't track the ball with your eyes in over that distance that quickly. Oh, Jake Arrieta, Cubs. Oh, wait, hold on. Oh, wait a minute. I'm missing. Oh, sorry. Okay, I got to show you this video here. Hopefully it works. Here we go. This is Jake Arrieta. So this is two pitches superimposed on each other. His cut fastball, which breaks into a left-handed hitter, and his four-seam fastball, which mostly is straight. Notice that so one pitch ends up down here, and the other pitch ends up over here. You know, they differ by, this much, which is a lot. And those two pitches look more or less identical until it's too late to react, completely too late to react. So this is, people who do baseball analytics, this is one of the things they look for. Good pitches, one of the ways that they fool hitters is by making every pitch look like every other pitch for as long as possible in the trajectory, so that by the time the pitches diverge from each other, the batter has already committed himself and is not able to react in time. And this is a good example of that. Okay, so I've already said that. All right, so now another Cub thing, spinning out of control. Okay, so this is something that happened in the National League Championship Series, the Cubs against the Giants last year, Game 5. Kris Bryant hit a fly ball to center field, and Joc Pederson, the center fielder for the Dodgers, notice he's turned one way, turns around, and turns back again. He made a complete 360. I call this spinning out of control. Okay, so when I saw this is one of those times where when I saw this, I said, oh, I think I know what's going on. And so, so I did some calculations and wrote an article. So this reminded me of something that had occurred in the 2012 National League Championship Series, where Hunter Pence hit this ball. Notice the shortstop for the Cardinals, Pete Kozma. He breaks to his right, and then he realizes the ball's going to his left. The bases were loaded. He got a double, and effectively this ended the game. I mean, effectively. I call it Hunter Pence's triple-double. Hunter Pence was the batter. Okay. In both cases, the fielder broke the wrong way. First broke one way, and the ball broke the other way. Why did that happen? Okay. So there are two physics issues here. One issue is, how does spin affect the flight of the ball? And then two, how does the batter put spin on the ball? So the batter, during the ball-bat collision, the ball comes off the bat spinning in a certain way. That's the second issue I said. And then that spin affects the flight of the ball, apparently in a way that the players in these two cases did not expect. Okay, so let's talk about that. We have to give you a quick primer on the aerodynamics of a spinning ball. Ball is going through the air. It experiences three forces. Gravity is pulling it down. It's going through the air like this. It's spinning around like this. Air drag slows the ball down. Air resistance, if you like. And the key here is what is called the Magnus force on a spinning baseball. So the ball is spinning around like this. The Magnus force changes the direction of the ball. It makes the ball swerve, and if you want to know what direction it swerves, Look at the leading edge of the ball. So the leading edge is the edge here, okay, so the ball's going this way. The leading edge is turning up that way, okay, so, and that's the way the Magnus force is. So if the ball is spinning like this, if it's going towards you, it's going to break this way. If it's spinning like this, it'll break the other way. If it has backspin, it's up. If it's topspin, it's down. And of course, it could be anywhere in between. So that's basically it. So this is controlling the axis of the spin is how a pitcher varies his pitches, curveballs, fastballs, cutters, things like that, sliders. But it also affects the batted ball. The aerodynamics is all the same. So a few years ago, I did some experiments where I fired a ball out of a cannon that wasn't spinning, and it hit a pseudo bat here. This is a chunk of a wood cylinder that's basically the size of a bat that's rigidly attached here. And the ball hit above the center of the bat, and notice that it bounced up, and notice that it's spinning. And the goal of the experiment was try to quantify the relationship between the angle that the bat went and the amount that it's spinning. Okay? But the physics is actually fairly straightforward, about at least qualitatively straightforward. When the ball hits above the center of the bat, there's a component of the velocity of the bat, of the ball, I mean, that is, remember, this is a curved surface here, okay? So there's a component that moves up the face of the bat. The ball literally slides, you couldn't see it from the video because it's not high enough speed, but the ball literally slides along the surface of the bat. If the ball hits above the center of the bat, that sliding is up. And therefore, there will be friction that opposes that sliding, and that friction is down, okay? And it's that friction that gives rise to a torque that sets the ball spinning in the manner that it actually was spinning with backspin, okay? So, again, these things are pretty common in baseball. If you hit above the center of the ball, if the bat hits below the center of the ball or the ball hits above the center of the bat, you'll get backspin. If the other way around, you get topspin. You can also have side spin, and these lead to very familiar results. You get the same thing if you're out in front or behind, okay? Then the sliding is along the length of the bat, and you get side spin on the ball. And just, again, you watch any game and you see the following things. Balls hit the left field or right field tend to curve towards the foul pole. You see lots and lots of evidence for that when you watch a game. Topspin gives rise to tricky bounces in the infield. Backspin keeps the ball in the air longer. If you have a lot of backspin, you could have some very tricky pop-ups to the infield. Okay, so here are some examples. Here's a head-on collision, and the ball leaves the bat more or less without spinning. If it's a head-on collision, there's no sliding, so there's no friction, so nothing to cause the ball to spin. The ball more or less goes out roughly the same angle that it came in. This is Marco Scudero again. Here is Matt Holliday. And notice he hits under the ball, and if you look carefully, you will see that ball goes straight up in the air, and it's got a lot of backspin on it. This would be one of those tricky pop-ups. And here's one in which the bat hits above the center of the ball, and the ball goes down, and it's got topspin on it, so it's spinning like so. Other examples, line drives, as I said, curve towards the foul line. So again, if the batter is out in front, the ball is sliding this direction, so there's friction in the other direction, and the ball hooks. This is sort of what you mean by a hook. It breaks towards the foul line. Similar thing happens if you're a little bit behind, then it goes in the other direction, and then the nomenclature is different. This is called a slice, but a ball hit to the opposite field will also tend to slice. It breaks towards the foul pole. And you just watch any game and you just see many, many examples of this all the time. Here's a video. This is Xander Bogaerts from the 2013. You see the ball is curving that way, all right? And here's Hunter Pence again. All right, so foul balls curve towards the foul line, but not this one. Not this one. And that's why Pete Cosmo was fooled. He thought the ball was going to break to his right, and it broke the other way. Why did it break the wrong way? To answer that question, you have to, whoops, I'm going the wrong way here. To answer that question, you have to look at this collision a little bit more carefully. This is Hunter Pence again. This is the guy who hit the ball. Notice that the ball hits the bat, or the bat hits the ball 3 different times. 3 different times. And it's that unusual nature that caused the ball to actually end up spin the wrong way. If you look very carefully, the last collision occurs right near the end, and you can sort of see that the ball is spinning in the way that it not normally would spin. It has the opposite sense. Okay? Now, Pete Kozma didn't know that the ball was spinning the wrong way. He could not possibly tell without high-speed video that this collision was this unusual type of collision. And so, being a smart infielder as he was, he started breaking the wrong way. This is the way, the blue line is the way, this is Pete Kozma standing here. This is the straight line path. This is the way he expected the ball to break. He expected it to go this way, but in fact it went the other way. And before he realized it, he couldn't recover in time. And the bases got cleared. So I call it a triple-double. The triple part comes because the ball hit the bat 3 times. And the double because he ended up on second base. Okay. So he expected this should be 4 foot. He expected a 4-foot break to his right. He got a 4-foot break to his left. Okay, I want to talk about the Bryant. Let's go back to the one I originally showed you, the ball that was hit to straightaway center field. In fact, this is the actual trajectory of the ball. Nowadays, there's ball tracking radar that's in every stadium, and this is the actual trajectory on a scale where you can sort of see the big picture. And if you blow that scale up, if you blow it up horizontally like this, the ball actually started off going slightly to the shortstop side of second base, and it curved this way. Now, you might have expected, so balls hit down the line curve towards the foul pole, you might have expected balls hit straight away wouldn't curve at all, but they do. And why do they? The reason why they do is, now this is Kris Bryant, and notice that bat. The bat is right here. Notice that bat is tilted downward, okay? And it's the fact that that bat is tilted downward which leads to, if the bat were purely level, the ball would have come off the bat with pure backspin. But because the bat is tilted downward, it has a component of side spin to it, and that side spin gives rise to a slicing behavior. So again, this is something you could observe a lot. Balls hit to center field tend to slice. They go to the, so off a right-handed hitter, they tend to move towards right field. Off a left-handed hitter, they tend to move towards left field. That's what you mean by a slice. And so this is really what happened, okay? And experienced outfielders know about this, okay? Joc Pederson is a pretty experienced outfielder. Nevertheless, he got confused. He probably should have known better, okay? But he got confused. The interesting thing, though, the physics is quite fascinating because it involves two different things: the spin of the batted ball, okay, which involves the physics of the ball-bat collision, friction, and things like that, and the flight of the ball and how spin affects that. Okay. Next topic, swinging for the fences. So Ted Williams wrote a book, The Science of Hitting, and here is Ted Williams, who knew what he was talking about. This is just a gorgeous, gorgeous swing. Okay? Now, as I've already alluded to, nowadays in baseball stadiums, there is technology that's installed that allows you to virtually track everything in the game. Radar is used to track the baseball, whether it's the pitch ball or the batted ball. Cameras are used to track the players on the field. So, you could, all sorts of things that you weren't ever able to quantitatively study before, you can now study. So one of the things that people have realized is that you can study in a lot of detail, sort of posing the question, what constitutes a well-hit ball? Okay, so what I've shown you here is a sort of a heat map. And there are two important parameters on this heat map. One is the so-called exit speed. So this is, if you watch games on TV these days, now that these new technologies have sort of gotten in the mainstream, you find these words a lot, exit speed or exit velocity. The speed of the ball as it comes off the bat. As you might imagine, higher is better, okay? That, in many respects, that's what a batter's trying to do. He's trying to hit that ball as hard as possible, meaning as high an exit speed as possible. It's only relatively recently that people have been able to sort of quantitatively study the other parameter, which is the launch angle, the vertical launch angle. 0 degrees is straight ahead, 90 degrees is straight up, and various ways in between. So here what I'm plotting is the following. I'm plotting the probability that this is based on real data from, I think, the 2015 season. The probability that a batter gets on base, where red is good, that's probability of 1, blue is bad, as a function of exit speed on this axis and launch angle on this axis. So you can start to pick this apart and sort of get yourself familiar with what this plot is in the context of the game itself. So let's take a look at this. Here are balls that are hit very hard, over 100 miles an hour, at a fairly small launch angle, say 10 to 20 degrees launch angles. So they're not hit that hard. They're hit hard, but they're not hit high. These are line drives. Typically, those line drives will go for singles unless you happen to hit the ball in the gap, then it might go for a double. So these are line drives. These are largely extra base hits, home runs. So these are balls that are hit hard, okay, but hit at a bit bigger launch angle so that the ball carries further, okay? Typically 25 to 35 degrees is sort of optimum, you can see here. These are doubles, sometimes triples, and especially home runs. These things here are, things that are accidental hits in a way. They're not hit that hard. You see they're, 70s, 80s of miles an hour, but they're hit at such an angle, and they're hit softly and at such an angle that they just get over the reach of the infield, but fall in front of the outfield. So-called Texas League, soft line drives, bloop singles, those kinds of things. And, whoops, sorry, wrong way. And this is what I call the donut hole, okay? If you hit the ball, say, at a 25 or the 30-degree angle, if you hit it really soft, you're going to get a hit. If you hit it really hard, you're going to get a home run. But anywhere in between, this is going to be a lazy fly ball. I call that the donut hole, okay? This is an example of where hitting the ball harder does not help you. You don't want to get caught in the donut hole. Mostly batters are trying to hit the ball hard, and more are trying to paying very close attention to that launch angle, okay? Trying to hit extra base hits, because that's where the money is, okay? Now, there are other ways to see this. This is the same plot, just shown sort of in you can see the mountain here, okay? Here is the donut hole in here. Here is a side view. Here's the donut hole, home runs, line drives, bloop hits. And you could even make the whole thing rotate. I use root for this for high-energy physicists and obvious. Okay. All right. Now, it's actually, so it's kind of interesting to look at this. Here's a ball hit 95 miles an hour, 10 degrees. These are the line drives. You see, the line drives are hit hard. They're hard enough to get over the infield and fall in front of the outfield. They're hard hit balls, okay? Here is the bloop singles. Here are the things that fall in the donut hole. It's just a lazy fly ball, 320, 330 feet, and here are the home runs. Okay. Okay, so the question is, this sort of shows you what a batter is really, sort of the outcome of what a batter is trying to achieve. The batter's trying to get on base, he's maybe trying to get a single, a double, or home run. And to do that, he's aiming for a particular region of exit velocity and launch angle. How does he do that? How does the batter adjust his swing to optimize the outcome? To answer that question, you have to define what you mean by optimize. So if you're trying to optimize your probability of getting on base, you want to hit the ball hard, okay, and you want to hit it in the sort of the 10 to 15, maybe 20 degree range. Those are the line drive singles. If you're trying to hit a home runs, you also want to hit it hard, but you want that launch angle to be steeper. And there is a third thing that pay attention to when you're talking about optimizing the swing, which is you're trying to minimize timing errors. And I'll tell you about that shortly. Okay, so these are the issues. And basically there are, there are various things that the batter has more or less under his control. Timing, getting the bat in the right place at the right time. Swing speed, you generally want to, if you want to hit the ball hard, you want to have a high swing speed. Aim, where on the bat the impact occurs, both along the axis of the bat, okay, the sweet spot, and perpendicular, the height, okay, relative to the size of the barrel, and of course the swing plane. So here's a picture. I'm not going to dwell too long on this picture. The ball, the bat, the ball is coming in at some angle, typically 6 to 10 degrees. For a good fastball, it's maybe falling at about 6 degrees, just mainly due to gravity. If it's a curveball, which is thrown slower and has topspin on it, it's maybe a bit steeper, maybe 10, 12 degrees or so. But okay, so there's a descent angle. Here is the batter swinging the bat. Here is his swing plane. I call it the attack angle, okay? And there is an offset here. Notice that the bat is below the ball, okay? And these are the two parameters that really matter as far as, once you've got high bat speed, these are the two parameters that really matter. The attack angle and the offset, okay? And basically, if you want to hit the ball hard, you want to adjust that attack angle so that it falls along that dotted line. So you have basically a central collision. So the momentum of the bat is going right through the center of the ball. If you hit below that, like it showed here, there's going to be friction and you'll get spin on the ball, but in the process of getting spin on the ball, you're going to get less exit velocity on the ball. Okay? So there are two knobs, if you like, that a batter can adjust. He can adjust his attack angle and he can adjust the offset. The swing plane and the aim, okay? And there are two outcomes he's trying to achieve with those two knobs, exit speed and launch angle. Okay, so now here is, these are calculations, okay? This is not data, okay? It's very hard to come up with real data on this, but it's calculations based on data, okay? Here is attack angle, here is offset. So half an inch, 1 inch. Here is the attack angle. 0 degrees would be perfectly level, 10 degrees, 20 degrees, 30 degrees. So this contour here, okay, the highest exit speed falls right along this line here. That's the case where this attack angle coincides with that center line angle, okay, and that'll get you the highest exit speed. So this is what what in the lingo of baseball you would call a squared up collision. The ball and bat are squared up with each other, and you get the highest exit speed that way. Okay, now that's exit speed. Now this is launch angle. This is how the launch angle depends on these same two parameters. The launch angle does not depend very strongly on the attack angle, interestingly enough. It depends mainly on that offset. Okay, I won't go into the reasons why that is, but it is the case. So now let's superimpose those two things. This line gets you the maximum exit speed. This is the contour from the previous plot that'll get you a 10 to 15 degree launch angle. Okay? And so if your goal is to hit the ball hard, so it would be along that line, at 10 to 15 degrees, in order to get on base with high probability, you would want to be in this region of that space right here. Namely, you'd want to have an offset of about 0.6 of an inch, and you want to have about a 10 degree attack angle. On the other hand, if your goal in life is to hit a home run, you want to be in the 25 to 30 degree range, and that's this blue contour here, and you want to hit the ball hard, and you see that's more like 1 inch and about 20 degrees. I call this the batter's dilemma. The batter has to decide what is it he's trying to optimize. Is he trying to optimize this, or is he trying to optimize that? And his swing plane, especially the swing plane, it will matter a great deal whether whether his goal is to try to get on base, which would give you a much lower swing plane, or the goal is to hit a home run, which would give you a steeper swing plane. Now, so the batter's dilemma. So now, in practice, the batter has a fixed swing plane, and his ability to aim, okay, that's the offset, that's more or less random. I mean, you know, sometimes he's going to get it right, sometimes he's not. The maximum exit speed, of course, will depend on the launch angle. So if the batter has just take a look at this plot. So here are the two different hitting strategies. If the batter swings at a 10-degree launch angle, you see that it intersects this black line at a launch angle of 10 degrees. Whereas if the batter swings with a steeper swing plane, it's more like 20 degrees. So in fact, these are actual data, again from the 2015 season. Kris Bryant versus Jose Altuve. Altuve, at least in the 2015 season, was largely a singles hitter. He actually last year hit more home runs. And you can see their two hitting strategies by looking at how their average exit speed depends on their launch angle. Bryant's peaks at a steeper launch angle, meaning he has a steeper swing plane. He's going for the fences. Whereas Altuve is really trying to hit singles, okay, and his swing plane is a lot lower, more like 10 degrees or so. So you could actually learn, you can sort of reverse engineer by looking at a player's data and try to figure out what that swing plane is. Okay, so Altuve has an on-base swing and Bryant has a home run swing. Now there's one more aspect to this that I want to touch on, which is the timing issue. And you can appreciate the timing issue in the following manner. So here is the ball coming in. I've exaggerated the angle here. So remember, it's maybe a 6-degree angle. If the batter swings up at a 6-degree angle, suppose he's aiming to try to hit the ball like right here, okay? Basically head on, okay? Head-on collision, squared up. And suppose he's a little bit ahead or a little bit behind. If his swing plane is the same as the descent plane of the ball, the timing error won't make any difference to him. He'll be squared up here, here, and here. The range of timing errors that are sort of forgiving for him is rather large. On the other hand, again, the ball is coming in at this angle. Suppose the batter has a, quote, a home run swing. This is what he's aiming for. He's aiming for something that's squared up here. But he's a little bit behind. Notice now the bat is way under the ball. He's going to hit a pop-up. And in this case, the bat is now over the ball. If he's way out in front, if he mistimed it, he's going to hit a weak grounder. And it doesn't have to change by very much, okay? The timing could be off by something like, this is rough, you know, you could change things by 0.004 of a second, which is like nothing, okay? And go from basically hitting a home run to hitting either a weak grounder or a weak pop-up, okay? So that's another way that a batter would try to optimize his swing, which is to make the swing level in the sense that the swing of the bat, the swing plane of the bat matches the downward descending angle of the ball. Batters, again, are paying much more attention to these kinds of things these days. Of course, Ted Williams understood this long ago when he talks about it in this book. He may not have understood about friction and this and that, but he certainly understood this point. Okay, I have just enough time for extra innings. Rocky Mountain High, I want to talk about the aerodynamics of batted baseballs. Okay, let me skip this one. This is not important. Barry Bonds hit a 756 home run back in August of 2007, August 7th, I think even. And it was the one that broke Hank Aaron's record for most home runs for a career. This is the trajectory of his home run. It traveled about 430 feet. Now, and once you know that trajectory, then you can create a model with lift and drag and all that sort of stuff. And then you could say, all right, now let me just calculate the same trajectory, but let me remove air altogether. What if this took place in a vacuum? that same ball would have ended up close to 700 feet from home plate. Air drag matters a lot, okay? Likewise, spin matters, but doesn't matter quite as much. This ball had some backspin on it, about 1,300 RPM of backspin. If I turn off that backspin, it travels maybe 40 or 50 feet less. It matters too. It doesn't matter anywhere near as much as the drag does. So drag matters. And that's why things are so different in Denver, because there's less air drag in Denver. In Denver, the air density, the drag is directly proportional to the density. The air is thinner. The air density is about 80% of sea level. So basically, the baseball carries further in Denver. So Denver is a pitcher's nightmare, okay? Drag matters a lot. The Magnus force of the spinning baseball matters, but matters less. So here, again, data, real data. I love data, okay? You know, when you have data, it confirms things that you thought you believed. So here is every major league ballpark, and this is the average distance of a fly ball that was hit between 101 and 105 miles an hour, between 25 and 30 degrees. These are balls that typically would be home runs. And major league average, other than Denver, is right around 405 feet, or 401 feet, this red line. You know, there's some of more than others. Look at Denver up here all by itself, 430 feet. 30 feet, that's a lot, okay? That is a huge amount, okay? So as I said, it is a pitcher's nightmare, Denver, 30 feet. And you could do the same thing here. All right, so a bunch of years ago now, this was realized from day one in Denver. Everyone knew this was going to be the case. They tried to, quote, level the playing field by playing around with the ball a little bit. One of the things about Denver is that it's very dry in Denver in the summertime. The ball dries out, and when the ball dries out, the bounciness of the ball actually improves. You actually can the ball can be hit harder. The so-called coefficient of restitution of the ball is higher when it doesn't have a lot of moisture in it, okay? Conversely, if you put moisture in it, it'll get worse, and the ball won't be hit as hard, okay? So by putting the balls in a humidor at a fixed temperature of 70 degrees and a 50% relative humidity, which is higher than the typical 30%, you're going to make the balls, quotes, mushier. It's not going to be as bouncy. And the question is, what effect did that have on home runs in Denver? And the answer is, pre-humidor, there were roughly 3.2 home runs per game. Post-humidor, this is up through the 2010 season when I did this analysis, 2.39 home runs per game, about a 25% reduction. So here's the physics problem. Can we use whatever physics we know to account for that 25% reduction? And this is sort of a classic example of sort of how a physicist sort of thinks about these kinds of things. So that's why I wanted to tell you about it. Can we account for the reduction? First question, how does the elevated humidity affect the bounciness of the ball, the so-called coefficient of restitution of the ball, and therefore the batted ball speed? Okay? And how does the reduced batted ball speed affect home run production? You know, this is a physics question. This is largely sort of almost a statistical question. Okay? All right, so various articles have been written about this by various people, including me. This is our work that we did. And home runs and humidors, applying the scientific method. Okay, so we started off, me and my collaborators, measuring the bounciness, the COR of the ball, as a function of the relative humidity. So we're able to quantify how much that bounciness, that coefficient of restitution, changes when you change the relative humidity from 30% to 50%. Okay? Then we had to sort of use real physics, the physics of the ball-bat collision, to take that reduced coefficient of restitution and from that determine how much reduction in the exit speed of the ball did that correspond to. And then we needed a trajectory model, again, more physics, to talk about how the distance of a fly ball would be reduced by reducing that exit speed. And then finally, we had to use information about fence distances then to talk about how many home runs were what was the reduction in number of home runs. So when we did this, we ended up with a number that was so close it was embarrassing. Okay? I mean, we had no right to get it this close, but we did. I mean, it just meant that the physics was essentially right. The actual reduction was 25%. We calculated 27%, but with a sort of an error bar, which is about 4%. All right, fine. You learn how to say yes for an answer, okay, and you call it quits and you go home, okay? But then, shortly after we published our paper about this, I got a phone call from a reporter at the Arizona, whatever the newspaper is, Arizona Republic. Okay, Nick here from the Arizona Republic. And this appeared, Arizona Diamondbacks Chase Field could become pitcher's haven with humidor. Now in Phoenix, which is where this is, the humidity is even lower, it's like 20%. So the reduction in home runs by storing balls at 50% would be even more. So he called me up to tell me that the Arizona Diamondbacks were thinking about doing this. And I told him about my paper, and I said, hey, we'll just use the same method and we'll figure out what's going to happen. And we calculated there would be a 37% reduction, not the 25% as in Denver, but 37%. Oops. And then, finally this, Arizona Diamondbacks back off using the humidor this year. I like to think that there is some causal relationship here. Maybe there was, maybe there wasn't, but if so, I'm proud of it. Okay, so in conclusion, I've given you lots of examples of how physics enters the game of baseball. I've covered just a tiny fraction of them. You can go to my website and you can sort of see all the different things that I'm involved with. Send me email. I'd love to talk about this stuff. Follow me on Twitter if you dare, et cetera, et cetera. And by the way, tomorrow, my wife and I, since we're in town for the couple of days, we're going to go see Hamilton. Okay, thank you very much. I don't know how to turn this off, actually. Thank you. So I'm very happy to take questions on absolutely anything. I've been told that there's a microphone somewhere, and you should, if you want to ask a question, there's a microphone right here. Please step up to the mic so everyone can hear you, and I'll be happy to answer your questions until I run out of steam. Don't be shy. Oh, come on, you must have some questions. Do I have a book out? I do not have a book out. One of the books that I showed you at the beginning by Cross, Physics of Baseball and Softball, I actually started out as a co-author on that book, and then I dropped out because I just couldn't get interested in writing a book. But he actually told me recently that they want to come out with a second edition, and maybe I'd be involved with that. So it's possible I'll work on that. But I'm just too busy doing things to... It's more fun to do things than it is to write about, you know... Anyway. The teams have a team physicist. There are physicists, there are people with physics backgrounds on teams. I know of a couple, the one for the Tampa Bay Rays and one for the Houston Astros, and there might be more. I haven't yet persuaded anyone to hire me, not that I'm interested in having a full-time job, but I think physics is a somewhat underappreciated skill set to have for baseball teams. I certainly get asked questions an awful lot from major league people, but no one's hired me.
Not very scientific. You have these trackers you could watch now.
Right. Anyway, some teams have physicists. Yeah.
I had a question. If they switch to the radial bat, do you think that would decrease the slicing and the hooking?
No, I don't think so. The radial bat, the radial bat is the one in which there's different kinds of wood. If you go around the circumference, there's wedges of wood. What that does is prevents the bat from breaking. That's the main thing that it does. And I think having such a thing is a good idea. I don't think I don't think it'll do anything as far as the hooking and the slicing is concerned, though, which is a property of the surface of the bat, you know, the friction between the ball and the bat. But you know, Major League Baseball has these rules that they sort of hang by religiously almost, and the one rule is that a bat should be made out of one piece of wood. And so, but I think the radial bat is a very good idea because you see injuries that come about because of, you know, that Hunter Pence thing I showed you with the bat breaking, but you see bats flying into the stands and hitting. Well, there was a third base coach for the Cubs a few years ago that, was it a coach or somebody got hit by it was a player, that's right. He was on third base, I think, yeah. Yeah. Anyway, so maybe it'll happen, but I don't think it'll reduce the hooking or the slicing, though.
You talked a lot about the effect of the spin off the bat.
Mm-hmm.
What impact does the spin that the pitcher imparts have when it hits the bat?
That's an interesting question. How much does the spin of the batted ball affected by the spin of the pitch ball? Is that basically what the question is? As it turns out, not a lot, as far as I can tell. That is, you do experiments. So I showed you the experiment where we were firing the ball. And so you can use those experiments to sort of fine-tune your model for the ball-bat collision. And when you do that, the way it turns out, and it's not obvious that it would turn out this way, but the way it turns out is that the spin of a batted ball is not affected a great deal by the spin of a pitch ball. It's an interesting result, and I can't give you an easy answer for why it is. It just numerically turns out that way. It's just simply not an obvious thing.
So my question is somewhat parallel to the last gentleman's question, but how does the speed of the pitched ball impact the launch speed of the batted ball?
Good question. Okay. In other versions of this talk that I give, I actually talk about that. Roughly speaking, the exit speed of the ball for a perfectly squared up collision, exit speed of the ball is about, if you take the bat speed and multiply it by 1.2, and then take the pitch speed and multiply it by 0.2, that's the exit speed. So bat speed matters a lot more. So for example, if you were to change the pitch speed by 10 miles an hour, which is a lot, you would only change the exit speed by about 2 miles an hour, which is not much. So it doesn't, and I think this is something that a lot of baseball people even don't really fully appreciate. You know, they always say, well, the faster it comes in, the faster it goes out. Well, okay, but you know that you can hit the ball very far, hitting the ball off a tee where there is no pitch speed. And you know that you can't hit the ball very far at all if you're bunting it where there is pitch speed but no bat speed. So that's the analogy I like to give. And so pitch speed matters, but it doesn't matter anyways nearly as much as bat speed does. Good question.
Do batters seem to be adopting the kind of launch angle that you suggest?
I'm sorry, say that again?
When batters want to hit a home run, are they using the kind of launch angle that you suggest? And do they change the angle when they're after a hit?
I have heard tell that that's the case. I have not talked with anyone personally about that, but so there is a hot debate going on. It was even going on earlier today. It was going on a lot of last year, but literally today on my Twitter feed, I was answering questions like crazy. In the last year, there has been a significant increase in home runs in Major League Baseball. And people have been trying to figure out why that is. A lot of people say, well, it's the ball. The ball is juiced. By juice, they mean this coefficient of restitution, this bounciness is sort of artificially jacked up so that the ball comes off the bat faster and you get more home runs. But then some people say, well, it's not that. It's really that batters are trying to hit more home runs, having a greater appreciation of the value of this launch angle. Okay, that they're changing their swings in order that you hit more home runs. Now, there's a penalty for doing that. You'll hit more home runs, but there'll be, the penalty is this timing penalty that I was talking about. You will hit more home runs if you time it right, because you're going to get the right launch angle. But if you mistime it, you're probably going to have more swings and misses or foul balls or pop-ups or weak grounders. But I think that there seems to be some evidence that batters are trying to hit more home runs by changing that swing plane, by making it a bit steeper. But it's indirect evidence. I mean, no one's measuring the swing plane. Well, should I give him my phone number? More questions?
Some bats have a hollowed out end. I don't know if you can use those in the major leagues, but you know what I'm talking about?
Yes. So, well, you mean the cup?
Yeah.
Oh, yeah, there are rules about, so the bats are cupped out. A lot of batters use bats. If you look at the very end of the barrel, there's a cup. And there are specific rules about that, of how deep you can go. And they do it simply to reduce the weight of the bat. The weight in that, well, I think what they're trying to do is, this sort of gets into the whole discussion about corking the bat, which some of you may remember from Sammy Sosa's days here in Chicago. You know, the idea of corking a bat, this is an illegal act, okay? You drill a hole into the barrel of the bat, along the barrel of the bat at the center of it, about an inch deep, an inch in diameter, maybe a foot deep, 10, 12 inches deep. And the idea there is that you reduce the weight of the bat so you can swing the bat faster, but it has a downside because there's less weight behind that collision. And when Sammy Sosa did this dastardly deed back in 2003, my phone never stopped ringing for 2 solid days from people calling me up about it. And eventually did some fairly careful calculations and experimental work and concluded that if your goal in life is to hit the ball as hard as possible, corking the bat is a net losing proposition, okay? What you lose in collision efficiency because you've reduced the weight of the bat in the barrel where it counts, what you lose more than compensates for what you gain by a higher swing speed. On the other hand, there are good reasons for corking the bat and therefore for cupping the bat. And that gives you, in addition to higher bat speed, you get bat quickness. That is the ability to get the bat from the initial position into the hitting zone as quickly as possible, which allows you to maybe wait a little bit longer on the pitch, allows you to make adjustments to your swing once you've begun the swing and you get a little bit more information about where the ball is going. So yes, some batters are using the cup bat at the end, and as I said, there are very specific rules, which I don't remember now, about how deep you can go.
Is there a kind of a catapulting effect of the cork?
So you said in the beginning.
That's a good question, by the way, but I'll get to it in a second. Yes.
So you said in the beginning that if you're swinging the bat and you let go of it at the last second, it wouldn't matter. What happens if you're bunting?
Ah, interesting question. All right, yeah, it does matter when you're bunting. Because, so the key here is that when you're normally swinging the bat, your hands are far away from where the impact region is. If the bat were shorter, or if the bat were, say, a tennis racket, okay? In tennis, it does matter. The grip matters for 2 reasons. The bat, okay, the thing you're hitting is shorter, okay? So the time it takes the pulse to go up and down again is a shorter amount of time. Plus, the collision time is longer because the strings of the tennis racket make the strings stretch, and that lengthens the collision time. So if your hands are right near the hitting surface, for sure your grip is going to matter. Absolutely. Okay, so there was this question.
Yeah. If grip doesn't matter and you can't muscle the ball, is there any advantage to the axe handle?
Yes, so nowadays there are a handful of major leaguers, I think even a growing number, that are using a bat the so-called axe bat, in which the handle of the bat is like an axe. So it's not a cylinder, it's asymmetric, like an axe. There is no conceivable way that I could imagine that the axe bat makes any difference at all as far as what happens at the impact is concerned. What it does is it makes the bat much more easy to grip and swing for the batter. And in particular, it helps prevent so-called hamate injuries, injuries to the bones in the hand, because it's a more comfortable grip. Your hand fits nicely right in here. It probably also helps prevent you from rolling over. You know, if a batter gets too far out in front, he tends to roll the wrists over, and if that happens prior to the collision, that's not a good thing. But this helps suppress that, I think. Did I answer your question? Yes, thank you. Oh, okay.
Like the tennis racket with the strings,
yeah.
Does the cork have a catapulting effect on, shooting the ball off the bat?
Yeah, that's an interesting question. That's exactly the question I asked the day Sammy Sosa did what he did. So in a tennis racket, the fact that the strings stretch like that gives you what is called a trampoline effect by a lot of people. You get the same thing in a golf club, in a driver, which is not a solid piece of wood. It's metal with a thin plate on it, and when the club hits the ball, that plate compresses and trampolines back again. And same thing with a hollow bat. So with a hollow bat, like aluminum or a composite bat, you get this so-called trampoline effect, which is largely the reason why, left unregulated, those bats grossly outperform wood bats. It's that trampoline effect which gives you basically a higher coefficient of restitution. Okay, so the question you asked is, does corking the bat give you a trampoline effect? And so my gut instinct was no, but there's no substitute for doing measurements. So I got together with my collaborators, we actually did measurements on it, and there's no trampoline effect. Yeah. But it's a good question to ask and a good question to try to answer.
This question might be more appropriate for a neurobiologist than a physicist, but I'll ask you nonetheless. So obviously you're familiar with the old adage, the hand is quicker than the eyes. As one who never went beyond Pony League baseball and has gotten in batting cages to face Major League pitching, for me it's largely guesswork. I suspect for professional players it's a little different. So could you address the mental side of a player who only has a fraction of a second? Is the process of trying to hit the ball in a particular way more a question of calibrating or anticipating the pitch in advance, or is the batter actually making a series of mental adjustments as the ball's coming in at him and obviously moving all over the place at, say, 95 miles an hour?
Yeah, I'm really terribly unqualified to do anything other than guess on a question like that. There are some players who say they guess. They actually admit it. I'm guessing fastball, I'm going to, and if it's not a fastball, I'm going to look foolish, okay? And then there are some players who try to pick up, for example, the spin of the ball. I don't have a ball with me, but, pitchers who go between fastballs and sliders, people talk about the red dot. When when the slider is thrown, the ball is spinning in such a way that the spin axis passes right through a seam. And so the batter actually sees this red dot. The ball is spinning around that fixed point, and you see a red dot. And when you see that, you know it's a slider that's coming, and you can try to adjust to it. But I don't know the answer to that. But the question is a fascinating question, and people are actually trying to study these things using virtual reality kinds of things, little experiments that you can do on a computer where you ask players to react to what they see and try to anticipate or guess or whatever it is they do. And but look, I'm not an expert. I'm really not an expert on that. Where's the mic? Oh, okay, sorry.
Okay. What about when hitters want to hit the ball to opposite field? How does that affect your model? Or does the physics change at all?
No, the physics doesn't really change. I mean, the physics of the collision, the physics of the ball-bat collision, no, it doesn't change. I mean, the physics is really all the same. The details, of course, are different because the physics depends on the angle. So if this is the bat, the axis of the bat, and the ball is coming in, it depends on what that angle is, and it depends on how mismatched they are vertically, and it depends on the speeds, and pretty much that's it. I mean, it depends on those things. And so the physics doesn't change. It's just the implementation changes a little bit.
Taking all the factors into account, should people probably use a lighter bat that they can swing faster or a heavier bat for them, for what they perceive?
That's an interesting question too. I think it depends on yeah, I think it depends on what it is you're trying to do. If you view yourself as being sort of a line drive hitter, some guy who tries to always square up in the ball, is not swinging for the fences, is simply trying to get on base, I think a lighter bat is very, very helpful. So if you look, a lighter bat will mean basically is going to mean your exit speed is not going to be quite as high as it is if you use a heavier bat. Okay? In other words, you're going to be able to swing the bat faster, but you're going to suffer a penalty. It's the same as the corking argument, because the collision efficiency is not as high. But if you look at these, let me just show you here. If you look at the, see if I can find it. Yeah, perfect. Here it is. If you look, you see that if you're trying to hit a home run, you've got a fairly narrow range of exit speed that's going to get you a home run, but you've got a much wider range of exit speed that'll get you on base if you hit it at a low launch angle. So if your goal in life is to get on base, I would say use a lighter bat. If you're trying to hit home runs, you're probably going to want to go with a heavier bat.
All right. With the eyesight and different things, how much difference does LASIK eye surgery help or hurt a pitcher or batter?
See the ball, hit the ball.
Yeah.
See the home plate. I don't know. It's got to help, right? I mean, if you can, you've got to be able to see the ball to hit the ball. I think at least you've got to see. You've got to see some of the trajectory of the ball to hit the ball. In pitching, I'm not sure. I'm not sure how crucial eyesight is for pitching. That's a harder question. But hitting, I think it's crucial.
Just a quick question. So what part of your formula did the PED affect? Or did they at all? Like Barry Bonds was a good hitter before he took them.
Yeah, so performance-enhancing drugs. I actually once did a calculation about this. So the more muscle mass that you have, if you put on muscle mass as a result of using performance-enhancing drugs, basically you're going to be able to swing the bat faster. And if you can swing the bat faster, you're going to be able to hit the ball harder. Or, I mean, that's one thing you could do with your increased muscle mass. Another thing you could do with your increased muscle mass, which gets to the earlier question about the bat weight, you might choose to go to a heavier bat and swing at the same speed. But the heavier bat is going to be more effective collision. But that's the way it's going to help you. It's going to help your ability to swing the bat. Of course, once the ball leaves the bat, so it's going to affect exit speed, presumably. And once the ball leaves the bat, of course, it's physics takes over and there's nothing you can do about it. Am I answering the question that you're at?
Because you look at like Kris Bryant, who's not very big, but he's got quick bat speed. And then you look at Barry Bonds, who could hit home runs prior to the PEDs, and then alleged.
Yeah. Of course, swinging there are a lot of sort of small people who, who get a lot of home runs. I mean, Hank Aaron was not a particularly big guy, right? And swinging the bat is a complicated process where you're trying, and again, I'm not an expert, there are biomechanics who do this stuff for a living, but it sort of begins with the big muscles of the body, the thighs and the hips, and the idea is that you generate energy from those muscles, and you pass that energy along to ever smaller muscle groups, and when you do that, those muscles are moving then faster, and ultimately you're trying to transfer all that to the bat. And it's a complicated process because you've got the so-called kinetic chain. You're trying to, one muscle group is trying to transfer energy to another muscle group, and you don't want the muscle groups fighting each other, which would be very inefficient. So that to me explains why people who know what they're doing, even though they don't have a huge muscle mass, are able to swing the bat fast.
Okay, so given the same speed, given the same angle, and no air drag, which ball goes further, a top spin or a back spin?
With no air drag?
Right.
There's air, but there's no drag.
Would there be a difference in the distance that a top spin ball would go versus a
back spin? So when the ball is spinning with backspin, the so-called Magnus force is up. So it's basically fighting gravity. So it keeps the ball in the air longer so it travels farther. When it's top spin, the Magnus force is down. So it's as though gravity were bigger. So it's pulling the ball down further so it doesn't travel as far. So if you're trying to hit a home run, you want to hit it with backspin. But if you're trying to get a line drive single, I've always advocated for topspin. Because with a line drive, you want that ball to it's like topspin in tennis. You want that ball to get over the net and then take a nosedive, okay? Topspin is essential in tennis so that the ball just stays in the court. So in baseball, you want that ball to go over the infield but then hit the ground before the outfielder can catch up with it. So topspin is actually better for a line drive hitter.
So from a physics point of view, what element account for the success of a pitcher?
Ooh, what element from a physics point of view? Well, I don't know from a physics point of view, but just look, speed counts for a lot. Okay, nowadays, I mean, it's emphasized a lot. And I think this thing that people are really only now starting to appreciate about having every pitch look like every other pitch for as much of that trajectory as possible, so that whatever movement occurs late enough so that the batter can't possibly react to it. So people talk about late break in a pitch. Of course, there's no such thing as late break from a physics point of view. The break is sort of continuous. But to me, late break means not much break, okay? Because if the ball is breaking a lot, then the batter can more easily perceive that what it's doing early in the trajectory than if it's happening late. In fact, that was my hope. One of the slides that I skipped over, which I'll probably never be able to find. Let's see what I can find here. It's my Mariano Rivera side. So here is Mariano Rivera throwing his, a straight fastball is a dotted line. His cutter is the solid line. And these two pitches look virtually identical until about maybe 200 milliseconds from home plate when they start to separate. And they don't differ by very much, but they differ by just enough that if you're a left-handed batter, you're standing over here, here's the bat, instead of hitting the sweet spot, it hits, almost right on the label and the bat breaks. Mariano Rivera was brilliant at doing exactly this sort of thing with his cut fastball. And the thing I showed you with Jake Arrieta is sort of similar. Okay, that was a video, but this you can actually see real data.
I'll ask a question. Is there anything that you haven't figured out?
Oh, there's a lot that I haven't figured out. And in particular, I really is still trying to figure out why there were so many home runs last year. I mean, there's some qualitative reasons, but they don't, if you look at the data carefully, you find that there are things that are not consistent. So, you say, oh, suppose it's the ball that's juiced. And then you look at the data carefully and you find there are things that are not consistent with that hypothesis. So then you say, all right, suppose batters on the average are swinging at a higher swing plane. And then you find other things that are not consistent with that. So, yeah, I would love to know the answer to that. But there are many things that, so, I wake up every day and I say, all right, what am I going to do today? All right, what unsolved problem is there? And there's never too many of them, okay? There's always enough to keep me busy.
Okay, thank you so much for coming out, everyone.
Okay, enjoy it.